come up to the front and there'll be some spares if you want one. Does anyone else not have all of the sheets? Does anyone else need a sheet for everything? Okay. Now, I'll tell you now, proton NMR, which we're going to start off first with. Proton NMR, you'll hear a load of horror stories about it. People will tell you that it's the most difficult spectroscopy that you're going to encounter, that it's one of the toughest questions on the paper, and so on and so on and so on. And you know what? They are right. It is. Unless you do it my way, and then you'll find it is a whole lot easier. All right? So you do need to pay attention to what I'm doing here. You do need to pay attention to the way that I do this, all right? Because this is a way of making sure that you're able to do this, all right? We're going to go on to next week some tougher ways of doing this. Sorry, some tougher questions. And again, it'll come down to whether or not you follow this technique or not, as to whether or not it's difficult for you, okay? So there's a number of things which we need to know about here. Let's take a look, right? We're going to start off, in the previous two instances, I've noticed that there hasn't been a huge amount of hands up and so on, okay, but you may find that this provokes you into doing it if there are considerably difficult aspects to it, but we'll see possibly next time as well, okay? Right, that's what it stands for, NMR, nuclear magnetic resonance. And actually, they make use of this actual technique in hospitals. Does anyone know where it's made use of in hospitals? Any idea? Which kind of instrument might you be needing? Any ideas? Some kind of scan. Huh? It's not a CAT scan, no, it's one which is often confused with that. Any ideas? It's the MRI scan. Okay, MRI scan. So I think you can see why they might drop the first word. Yeah, right. Joe Public goes in and is told that he's about to undergo some kind of nuclear point, on his body and or hers, and decide that can make them very uncomfortable. So they drop the word nuclear. Okay, and they just go for magnetic resonance imaging. But it is NMR that they're doing on people's bodies at that point there. And what NMR does is it's able to actually look at certain atoms within the body, usually protons or hydrogens, okay, and we're able to get a map of the body when we look at the various different hydrogens throughout the body and different kind of environments they're in. Okay, NMR spectroscopy. Requirements for NMR spectroscopy, any type, and it's not just proton NMR that we deal with, okay? First of all, atoms contain an odd number of nucleons. Now, you've probably not come across that terminology before, nucleons, okay? Nucleons are particles where? In the nucleus, okay? So that means protons and neutrons, okay? Right, so we need an odd number of protons and neutrons, okay? That means that we can get NMR spectra from H1, okay? H1, we call that proton NMR, okay? By the way, hydrogen has got two other isotopes. So hydrogen has got two other isotopes, H2 and H3. Does anyone know what H2 is called? Hydrogen, by the way, is the only element to have other isotopes named differently. Does anyone know what H2 is called? Yeah. Deuterium. Deuterium, yes. Does anyone know what H3 is called? Tritium. Tritium, yes. So made kind of, common knowledge through things like Spider-Man and things like that. Though tritium is actually the hydrogen which was used in the first nuclear bomb, the first hydrogen bombs. Okay, that's why it's gaining notoriety. Okay, so we can get NMR of H1. Okay, we can get it of carbon 13. Yeah, it's odd again. and fluorine and phosphorus. All of those are odd numbers of nucleons in the nucleus there, okay? And so any of those, and we do NMR of all of those, okay? We will look at today proton NMR, but also on your syllabus is carbon-13 NMR. Carbon-13 NMR is a walk in the park compared to proton. So if you get your head around proton NMR, carbon-13 is dead easy. I promise you that, okay? All right, so you certainly couldn't get NMR spectra from hydrogen-2, which we've just identified as deuterium, okay? But we could for hydrogen-3, tritium. We could get it for that as well, right? We can't get it for the most common abundance of carbon, carbon-12, and we can't get it for its radioactive isotope carbon-14, but carbon-13 we certainly can. And around about 5% of all carbon out there is carbon-13, which is a substantial amount, and that's why we do NMR on it, because we can then find out an awful lot about whatever we're looking at, okay? All right, fine, so there we go. We are going to today consider proton NMR, okay? And like I said, later on we are going to consider carbon-13 NMR. But I did say that's dead easy compared to proton NMR. You can get your head around proton NMR, carbon-13 NMR will not be a problem, okay? Right, as I've already said, my way, and the way I do it in 2 steps, right? That's the trick. That's the way of doing this. So we're going to consider what I call low resolution proton NMR first. And only then will we go to high resolution proton NMR after that. Okay? And off your phone, please. At the back there. Thank you. Okay, so we're going to go from low resolution proton NMR to high resolution proton NMR. Okay? Okay, now a little bit of background to proton NMR spectroscopy, right? They might ask you a little bit about, well, exactly how does this work? Well, here's how it works. First of all, you need to be, or what you're looking at needs to be in what we call an external magnetic field. So generally, a pretty powerful magnetic field. We can form that very easily through electromagnets, okay? And so if ever you're in one of these machines which looks at you in a hospital, MRI scans, you'll hear a kind of a humming sound. Well, that humming sound is actually a very powerful magnetic field being applied to the person who's actually in the MRI scanner, right? What's going on there is protons, usually, I mean, you are 70% water, and therefore an awful lot of protons within you, hydrogens within you, okay? And those hydrogens are aligning or going exactly the opposite way to that external magnetic field, okay? So that's what's going on. Where they're aligned, so here, that is aligned with external, then that's in a low energy state, okay? If they are opposed, so if they flip, okay, well then they're a high energy state. These protons, you can think of them as tiny little magnets, tiny little bar magnets. And they can either line up or they can flip and be opposed, okay? Well, we can get them to alternate between this state and this state here simply by hitting them with some energy. Very little energy is needed to flip it from there up to there. And so that energy actually is in the very low energy section of the electromagnetic spectrum. Okay? So here, that's what's going on. Hydrogen nuclei, or any of these which can do NMR spectroscopy, they behave like tiny little magnets. Okay? They're aligned or they're opposed. Okay? And the opposed is the higher energy or the less stable state. So it's possible to get them to flip between these two states, right? How do we do that? The energy that's needed, well, it's only radio waves which are needed to do that. So if I hit this at the exact right frequency of a radio wave, it will flip up there. Yes?
The arrows, like going up and down, do they happen simultaneously, or is it like it either goes down or it goes up?
The vast majority of them will be in this position here until I apply the radio waves at the exact right frequency, and then some of the protons will then flip up there. And as they flip up there, that will absorb some energy. And where it absorbs that energy, we'll see that as a peak on the spectrum. So that's why we get all these different little peaks. Now, depending on where the hydrogen lies in the molecule, depends on the exact amount of energy it needs, because some of them have slightly different energies to others. Okay, and so we'll see that because we get a range of peaks on the spectrum there. So that's the background to it that we need to know a little bit about here, right? Okay, NMR spectroscopy then. We need to know about something called the standard. Okay, and the standard is used for measuring all of the other peaks, right? What we use is this stuff here, tetramethylsilane. Okay, and that's just given the name or the initials TMS, tetramethylsilane. Okay, that's it there. Okay, so tetramethyl, 1, 2, 3, 4 methyls on the silicon there. Okay, why do we have the silicon there? Well, the reason we have the silicon there is because it forces all of these protons here, all of these hydrogens here, to resonate at a slightly different frequency from if you had a carbon there. And why do we want that? Well, we want our peak, which is going to be the reference, to lie slightly away from all the other peaks. Otherwise, it would lie on some of the peaks which we're interested in, and it would mask them. So we need something which is going to be slightly away from all the other peaks so that we can measure according to it. All right? That's why we use that stuff there. Something to know here then. We're going to say that all of these protons here are in what we call the same environment, or the same chemical environment. And why are they all in the same chemical environment? Well, here's the reason, okay? Each of these hydrogens here is connected to a carbon, which is then connected to a silicon. And you can say that for this one, and for this one, and for this one. So all of them will give us one peak in exactly the same place, okay? Okay, so I said we're going to use the silicon there because it's going to give us a peak which is slightly away from all the others. Okay, and that means we can measure everything according to that one peak. All right, so let's take a look at this. And if we have a look here, this is an example here of a spectrum. It's not got anything on it at the moment, okay, but this is an example of a spectrum, okay? Right, first thing then. Proton NMR, we're going to measure peaks of protons against TMS, so that's our 0. Okay, so there's TMS right there, tetramethylsilane, and we're going to say that's 0. We're artificially putting it in. We artificially put it in at the same time as we put in our sample, so we can measure our sample according to it. That's the 0 right there. You see that peak? That's it there. Now, actually, that peak would actually be an absolutely massive peak. A whopping great peak, because it accounts for 3, 6, 9, 12 protons. So that peak there would actually be really, really large. But we don't want to see a really large peak on there. We only want to know that that's the position of 0. So all we do at that point there is we turn it down. So that peak would be a large peak, but all we do is we turn that peak down because we just say, well, all I want to know is where is 0 on here, but it would be significant. Okay, all of the other peaks appear downfield of TMS. Now what does downfield mean? That's what downfield means, okay? So here, 0 is here, and heading that way is downfield. All of the peaks will appear like that. Okay, and here, this is our scale, chemical shift, okay? And it's measured in ppm. The units are ppm, which is parts per million, okay? So this is our scale that we're going to use, right? Right, fine. So, this is what you've got on your handout sheets. I just want you, could you just go and find it? Okay, because I just want to point out a few little bits and pieces on here. So, if you could just have that data sheet. I think I said it was table B, right? So just have table B in front of you, right? Whenever you tackle NMR questions, proton NMR questions, you are going to need to have this in front of you, okay? So this is going to be something important to make use of, right? And I just want to point a few of these things out. So all of these here, all of these values here are downfield from TMS. They're all measured according to the zero there, right? We need this sheet when we're interpreting NMR, so don't try and do it without it. You'll always be given this sheet in the exam. Something to bear in mind, electronegative elements tend to drag peaks downfield. So if you've got oxygens, nitrogens, chlorines, bromines, then that's the effect. So have a look here, okay? I've got a proton here, which is reasonably close to an oxygen. And so it's at 2.1 to 2.6. If it wasn't next to an oxygen, it would tend to be one of these ones up here. So CH3 is 0.7 to 1.2. CH2 is 1.2 to 1.4, and CH is 1.4 to 1.6. But because there's an oxygen fairly nearby here, it's now more downfield, right? Higher parts per million. If it's directly connected to an oxygen here, then it goes even further, okay? Likewise, if I've got chlorines and bromines, it drags it downfield, okay? So this is a common pattern here. If you've got two electronegative elements here, okay, so the oxygen here has got two, for example, carboxylic acid. Now it's drawn it significantly far downfield. So here, carboxylic acid proton here has a range of around about 10 to 12 on there. So it's really been dragged significantly far downfield there. Okay, it's worth bearing in mind, it's a guide. You're not given every single possible circumstance that you could have on this table. So for example, if I had a molecule which contained 2 chlorines or 3 chlorines near to a proton, well now I don't have anywhere on here which shows that situation of 2 chlorines or 3 chlorines for that. So I would have to expect that if these protons here are affected by the chlorine to that extent, so somewhere between 3.1 and 4.2, if I had a second chlorine here, well then I could expect that to go up maybe to as much as 5.5 or even 6. And if there was a third chlorine or a bromine around, it might be even further again. It's a guide only, okay? When should you use those data values? Well, when you have something which actually fits exactly into those kind of situations there. That's when you'd be expected to do that. So for example, if I had an alcohol, okay, then an alcohol, okay, I would be expected ROH to have it somewhere between 0 and 5, okay? If I had, for example, a carboxylic acid, now you are going to be expected to quote a value between 10 and 12. Okay, and so on. So, for example, an aldehyde, okay, you're expected to quote that. But you're not always going to have an exact match, all right? Okay, fine. Something else I just noticed, OH protons and NH2, all for that matter, if you don't have a primary amine, if you have, for example, a secondary amine, so you've got 2 carbon chains attached, and so it's now NH, okay, they're what we call labile. And labile, well, that's going to mean that it stretches over a wider range. There's a greater chance of it simply cropping up somewhere. Now, in fact, the range is actually much more significant than that. They're being quite nice to you there. Okay, so you only have to quote a range of between 0 and 5, or 1 and 4 and 4.5 for alcohol or amines. Okay, but here. That's what we get for labile protons, all right? And one more thing about labile protons, okay? Labile protons, they only give us a single peak. That's an important thing which we need to know about. They will only ever give us a single peak, and that's really important when we come to look at high resolution. So they will not get split, and they will not undergo splitting. I'll talk to you about splitting when we get there, but I need you just to remember, labile protons are always single peaks. That's it, okay? Okay, fine. So let's go back to this, spectrum here, and we're going to consider this molecule right here, okay? That molecule there is methyl propan 2-ol, right? And if we take a look at that molecule, how many different chemical environments are there for that molecule? When we take a look at that, we can see there's 2. Where are they? The CH3 protons, 9 of them in total, so there they are. I'll put them all in red. Yeah. And we've got the OH proton, okay? One of those, that's in green right there. Okay, this is low resolution, what we're about to do. And this is the trick. You do this bit first, and then you do high resolution afterwards. So we're going to spend just a few moments getting to grips with low resolution. So you're going to need your data sheets in front of you. Okay, could you please just identify for me where CH3 protons should lie? So where should CH3 protons lie on our scale? Just somebody find that data sheet value for me. Go on, Libby. Yeah, 0.7 to 1.2. Can you see on your data sheets, the second one down there? 0.7 to 1.2. It should lie somewhere in there, right? So you'd be expected then to show a peak somewhere between 0.7 and 1.2, okay? This is what we're going to do. And because it's for 9 protons, it's going to be a pretty big peak, this. You also need to label it up, all right? So here, that is due to 3 CH3 protons there, okay? Please don't get confused about it being CH3, it's the protons there that we're interested in, right? Okay, fine. Where does my second peak lie then? Where am I going to find that? Where does that second peak lie, the green one now? So where will I find that? Go on, Joe. Yeah, it's the very first one on there, isn't it? Yeah? So you can see then that it is somewhere between 0.5 and 5. Okay, very frequently, alcohol proton crops up around about 4 to 5 actually. Okay, it can go anywhere. The reason why it can go anywhere along the point is because it's labile. Okay, so that's a very familiar place for it to be. And so look, we're going to show our other peak then at 4, and that is for that labile proton 1. And that, again, you need to label it up, is the OH, right? That's your low resolution spectrum, right? That's the low resolution spectrum. So that's how we do this, okay? So look, let's take a look at a few molecules here, okay? And let's just see if we can identify the number of different environments, okay? So for the first one, how many environments are there for that very first one? Two. Second one? 2 again. Third one? Okay, 3. Fourth one? 2 maybe? Well, I'd say there's 4. Come back and have a look, okay? The next one is 5. That was 4. That was 3. Let's go and have a look and see why they are. The first one, why is it 2? That's why. The CH3s are in the exact same environment as each other, okay? So here, why? That CH3 is connected to CH2. That CH3 is also connected to CH2. They're in the same environment, whereas of course CH2 is different. Okay, 2 environments there. There we go. That's why we have 2 environments for the next one. Okay, so very similar to the previous molecule. Those CH3s are all in the same environment. That H is different. 2 environments there, right? We come to that one. Now this one here catches a lot of people out, because of course that's CH2 and that's CH2. And people say, well, what's the difference? What is the difference? Yeah. Yeah. This CH2 has got a chlorine attached to it, whereas that CH2 is further away from the chlorine. They're in a different environment. So it's going to give us 3 peaks. And of course the CH3 is different again. Yeah? if we take a look at that, same idea here then. Look, here, don't forget the skeletal formula, you can't see all the hydrogens, but here, there is a hydrogen on here, and that hydrogen is very close to the bromine. The next closest are in a line here. Both of those two there are the same distance away from the bromine. And then here, in a line, that one there and that one there are both the same distance away from the bromine. And that's furthest away. So that's why I've got 4 different environments. The red, the blue, the green and the brown there. Okay? Of course, over here, same thought processing. You're going to have the same thing there, but then that is another environment again. So there you go. That's now purple. Okay? 5 environments for that. All right? Same logic here as with that there. But don't forget you've got the proton there as well. So there you go. 4 environments. And lastly then, 3 environments. Well, there they are. The carboxylic acid proton. Right, okay, so let's take a look at some of these in a little bit more detail, just to see what they're going to look like then in terms of their low resolution spectroscopy. So I've chosen 4 there, okay, that I just want to have a little bit of a look at. Where did we say we were going to find, in the top left one, where did we say we were going to find CH3 protons then? On your data sheet, where did we say we were going to find those? Second one down, wasn't it? 0.7 to 1.2, right? So there we go. And for the CH2s, well, where's that? If you have a look at the 1, 2, 3, 4th one down, can you see between 1.2 and 1.4? Okay, so there we go. 1.2 to 1.4. Notice the size of these here. 2 CH3s, that's 6. So the CH2 there. All right. So what you've got is a 6:2 ratio. Be careful. They don't have to say that to you. All right. Are you meditating? Keep your eyes open. Okay. So 6:2 ratio. Okay. They only need to show you a 3:1 ratio. All right. They only need to do that. Okay. All right. So. Here then, what have we got here? Well, CH3 is furthest away from the electronegative element. It's probably not going to be really affected here. You're probably going to find it between 0.7 and 1.2, right? The CH2, the blue one, is next furthest away. And again, it's unlikely to really be affected that much. It might be affected a little bit. So of that range there of 1.2 to 1.4, you might find it towards the top end of that range, around about 1.4, because it is getting a little bit closer to the chlorine. But the green CH2 is directly attached to the chlorine. Where will I find that? Where will I find that green CH2, please? Where have I got to find it on this data table? Somebody give me a value that I've got to see. Yeah? Yeah, you've got to. About halfway down, right, it shows here 3.1 to 4.2. That is directly connected to chlorine, and you are not going to be given any leeway on that. It will be an expectation that you pick that up and that you're not quoting a value around about here. That is now directly connected. You'd be expected to be identifying that. Okay, here then, there we go, there's our, notice how I have to now label up this as CH2Cl to make it really clear to the examiner that I mean those protons there connected directly to the chlorine, okay? So I have to do that in my labeling. All right, and we take a look at this here then. Okay, what have we got? This one's furthest away from the bromine. It's going to be nearest to TMS, okay? Next, well, the green ones are next. So they're going to be unlikely very effective at all. So almost lying on top of that one there. But as we approach the blue ones probably are going to feel a bit more of an effect from the bromine now. So notice there's a little bit of a gap now. You haven't got to be this on it, okay, but you need to just recognise that here there are 3 different environments here. And then the hydrogen here, connected to the carbon, which is directly connected to the bromine. Now you've got to, again, give that range, which was halfway down, somewhere between 3.1 and 4.2. There's, you're not going to be given any chances on that one there. Somewhere between 3.1 and 4.2. You've got to have it there, okay? Notice the values here. Well, it's a CH2, so that's 2. Then there's 2 lots of CH2s there and there, so that's 4. But then that's just the CH. So that's the low resolution spectrum for that molecule, okay? And finally then, for the propanoic acid, well, we've got then CH3. Why is my CH2 now there? Take a look. Why is my CH2 now there? What have we now got to identify? Which value is it now that we have to talk about now? Can you see it? 2.1 to 2.6. Take a look. 2.1 to 2.6. You now have a proton on a carbon next to C double bond O. Yeah? Proton on a carbon next to C double bond O. Can you see that? It's about a third of the way down, 2.1 to 2.6. And again, you have to be able to use this data table to identify these here. So here, there will be, that CH2 there, you will not be able to get away with putting it around about there. You have to recognise that it now is a little further down. They're going to be really picky about this. Okay, of course the carboxylic acid protein, that's dead easy to spot. It's right at the bottom, somewhere between 10 and 12, very easy, right? Okay, fine. And there we go. And again, you'll have to label them up. Okay, so here, it will not be enough to just go like CH2 here. You have to show it is next to a carbon double bond oxygen, yes? And here, it will not be enough to just go like OH. You have to show it as the carboxylic acid OH. You've got to label it up in that manner, right? All clear? Okay, fine. So, well, we've already spoken about this, okay, I'm not going to bang on about it, okay, labelling up, okay. But what does low resolution spectroscopy allow us to do? Well, it allows us to determine, first of all, the number of environments. So here, for this molecule here, ethanol, there's 3 environments, aren't there? 1, 2, 3 peaks, 3 environments, right? And it also allows us to know the number of protons in each environment. So 3, 2, 1 here. Though don't forget, they only have to give you the lowest possible ratio. So if you have, for example, a 6:4 ratio, they only have to show that it's 3:2, and so on, right? Okay. Now, this is where they're going to go then. This is what we've got to be able to do. Low resolution to high resolution. This is the trick now. Once you're able to do low resolution, we have to convert it, okay? So here's what now happens at high resolution, okay? High resolution proton NMR, we're now going to consider each of those peaks, and we're now going to split them, okay? How does the splitting take place? This is how. It is according to what we call the N+1 rule. And the N+1 rule, N is the number of protons on the next carbon. The next carbon, right? I did say to you as well, labile protons don't split or get split, so basically what's that mean? They always turn up as a single, or what we call a singlet, okay? So that's good, it means we've got less to worry about, okay? You're just going to write it down as a single peak each time for labile protons, okay? Right, let's take a look at this here, sorry, did I? Yeah, take a look at this here. So what we're going to do here then, we're going to take our molecule, ethanol, it's a nice easy one, right? And we're going to talk about this first of all at low resolution, and then we're going to convert it to high resolution. So let's just take a look at it at low resolution first of all. Okay, and we've already discussed this, so I don't intend to labour it again. We're happy with that being the CH3 at between 0.7 and 1.2. There we go, all right? there's the CH2, okay? Notice that it's CH2 directly connected to oxygen. So if it's directly connected to oxygen, well now it's the one above the one to do with chlorine and bromine. Can you see? Again, it's nearly halfway down, but it's between 3.1 and 3.9, okay? And I absolutely have to put it at that point there, and I label it CH2 connected to oxygen to make it crystal clear to the examiner. That's what I mean, okay? And then we've got ROH, which is labile. It can crop up anywhere between 0.5 and 5, but I did say a very familiar place for it to be was somewhere between 4 and 5. Well, there we go. There it is, all mapped out, low resolution. And now what we're going to do is we're going to now turn it up to high resolution on each one of those. So, they're going to get split. Okay. Red protons have 2 protons. So here are the red protons. Okay. Notice this. They are all the same. Right? They're all the same. So when we say the protons on the next carbon, we do not mean that and that being on the next carbon. I mean all of those are the same, and the next carbon along is that one. So how many protons are on the next carbon along? 2. They're the blue ones. Yeah? So here, the red protons, those ones there, have 2 protons on the next carbon. So n is 2. Yeah? Following the n+1 rule, that makes 3. And if it's 3, well, we say it's a triplet. Okay? So what happens? We're going to get rid of that peak, and we're going to replace it with the triplet peak. And the triplet peak looks like that. I'll show you exactly how we get that, but that is a triplet peak. We've simply got rid of the low resolution one, we've replaced it with high resolution triplet. Okay, fine. The next one then is this blue peak here. That's to do with those protons there. Now those protons there, on the next carbon we're looking for. So the next carbon, well, I should look that way and that way, but there isn't a carbon that way. If there were a carbon, I'd look at the protons on that one as well, but there isn't. So I'm only going to look that way. And if I look that way, I've got 3 protons on there. Following the n+1 rule, okay, that means 4. It's going to get split into 4, okay? So here, we call that a quadruplet or a quartet, okay? What does that look like? Well, we're going to get rid of that blue peak now and replace it with quadruplet, quartet. That's what it looks like, okay? Finally then, the green protons, well, I said the green proton was labile. That means it doesn't get split, and it doesn't split anything else either. It stays as a single peak. So there it is as a single peak. That is the high resolution spectrum for ethanol. If you try and do that straight away, it's very confusing. If you do the 2-step process, low resolution and then high resolution, you will find it an awful lot easier. Okay, you really will, okay? So it's very worthwhile mapping it out at low resolution and then high resolution, okay? Okay, fine. So let's take a look. Look, it's not in your specification to know these splitting patterns, but I always show them because the more you get to see them, the better it is for your understanding, okay? So single, doublet, triplet, quartet, quintet, also known as pentet, sextet, known as hextet, and septet, also known as heptet, okay? So here, they're useful to see. Where do they come from? They actually come from Pascal's triangle. So mathematicians, you'll know this, but look, Pascal's triangle, how do we get Pascal's triangle? All you do is you start with a 1 and you keep on going outwards that way and that way. And what you do with the numbers is you add them together to give you that number there. So 1 add 1 is 2, 2 add 1 is 3, 3 add 1 is 4, 3 add 3 is 6, and so on and so on, okay? That's what Pascal's triangle is, okay? It's useful to see here then because the singlet is, of course, just 1. The doublet, notice that both peaks are the same height, are 1 to 1. The triplet, 1 to 2 to 1 in terms of height, 1 to 2 to 1. Yeah? The quartet, 1 to 3 to 3 to 1, 1 to 3 to 3 to 1 in terms of height. Yes? See how that works, okay? And it goes all the way along. Notice that it's perfectly fine to call quartet or quadruplets, quintet or pentet, hextet, etc. Okay? That's perfectly fine. You want to follow those because those follow the naming system that you already have. Okay, that's perfectly fine, all right? Okay, so very common splitting pattern that I want to just identify for you because patterns in NMR spectroscopy can really help us, okay? If we take a look at this molecule again, okay, and if we take a look at its NMR spectrum again, that's what we ended up with, that high-resolution NMR spectrum, didn't we? But I just want to identify something very, very clearly on here. That's how you label it up. But notice that part of the molecule there, okay, that part of the molecule there, CH3CH2, connects to something which won't split. Right? It doesn't have to be an oxygen. It might be a carboxylic acid carbon, C-double bond OH. It might be part of an ester linkage. Okay, it might be a chlorine or a bromine or whatever. But if you have something here which won't split, then you will get this pattern. CH3CH2 is triplets, quadruplets in the ratio 3 to 2. And it's a very, very familiar pattern. And you know, if you want to find some easy ways of doing this, spotting patterns is a very helpful way of doing NMR spectroscopy, right? So here, that's what we get, CH3CH2X, but that X is something which cannot then have protons which are being involved in splitting, right? Okay, examples then, so just take a look here. There we go. That there is, in fact, propanoic acid, okay? Here's another one, okay? In fact, this is an ester, okay? But again, notice this. Even though there's a peak between the two of them there, okay? And likewise there. I mean, this time, the peak is nearly lying over the quadruplets, okay? But that very familiar pattern of 3 to 2, it tells me straight away that I've got a CH3CH2 in my molecule here. And there, okay? Again, all right? So very, very familiar patterns which will help us to be able to answer questions. So here's an example question then, right? NMR spectrum is obtained, okay, for two pure compounds in F, and they both have a formula C3H6O2. What type of molecules must they be then, if they are C3H6O2? So 3 carbons, 6 hydrogens, 2 oxygens. 2 oxygens, that must ring some kind of alarm bell for you if it's got 2 oxygens in it. What is it likely to be with 2 oxygens in a molecule? Go on. Carboxylic acid, yeah. And what's also isomeric with carboxylic acid? What type of molecule is also isomeric with carboxylic acids? Yes, esters. Yeah, so we've got here then either ester or carboxylic acid, okay? We've got 2 NMR spectrums, and what are our possibilities then, if we want to identify ENF here? Well, our possibilities are 3 carbons long, okay? Possible structure must be, of course, propanoic acid, 3 carbons long. But if I take the C-double bond O and drag it through the molecule, and then drag it through the molecule again, I'll end up with that C-double bond O on there, and then on there. So that will give me my other 2 structures. They're esters now. So my other 2 structures are, of course, dragging it through, so there's the C-double bond O now on that carbon there, okay? And if I do it again, if I drag the C-double bond O onto that carbon there it is, okay? So these are our possibilities here, right? Propanoic acid, methyl ethanoate, and ethyl methanoate, okay? Well, there's only 2 spectra here, and yet there are 3 possibilities. Can anyone spot straight away a very familiar pattern which may well help us out here? It's right there, isn't it? That one that I spoke about earlier. Okay, so there it is. But hang on. There's two possibilities for this, aren't there? If we take a look at this here, yes, it's there. CH3, CH2 connected to C double bond O. It's there, right? It's also there, isn't it? Yeah? So look, I mean, it is quite easy to see which of these it is, but the reason it's easy is because of that peak there, isn't it? And that peak at 11.7 tells us, because it's a singlet peak, okay, it tells us that that is carboxylic acid proton, and it's carboxylic acid proton. It's got to be this molecule here. But if they had hidden that from us, let's suppose they hadn't shown us that peak, yeah? Could we still have known? Could we still have known that this must be carboxylic acid? Can anyone tell me anything about this peak here? Notice it's between 2 and 3 here. Okay, so here it's about 2.2, 2.3 for that there. Okay, what does that tell you the CH2 is connected to? What does it tell you it's connected to? Because it is around about there. So CH2 there, it's around about 2.2, 2.3. Have a look. It's your 1, 2, 3, 4, 5. It's your sixth one down there. Notice that range 2.1 to 2.6, okay? And that is for this. Here, the protons are next to C double bond O, yeah? What about if it had been this one? Well, now the CH would be next to O. Where would this shape here now be? Where would it now be? Say that again. Go on. It would be. Can you give me an exact number? Or between the range? 3.1 to 3.9. Yeah? So now, that shape there would now be in there. So, and this is the subtlety to it. Because they will do this. A favourite question of theirs is asking about esters. The ester linkage is C double bond O. But if you have the protons one side of the ester linkage, it's going to be between 2 and 3, there. If you have it on the other side of the ester linkage, it's going to be between 3 and 4, there. And they're going to explore that, they're going to use that against you. It is a favourite question of theirs to see if you can identify whether it's directly connected to oxygen or connected to C double bond O, the other side of that ester linkage, right? Okay, fine. So, there we go. Why was this one here? Well, can you see those 3 protons there are connected to oxygen, so they're not going to get split. And these 3 protons here are connected to C double bond O. They're not going to get split. So there's a singlet peak and a singlet peak. Why are they written 1 to 1? Well, of course, that's going to give you 3, that's going to give you 3, and a ratio of 3 to 3 is, of course, 1 to 1 as its lowest. So that is that molecule there. Right, okay, we'll stop there.